what do you think meta learning is and looks like now in the 5 years, 10 years? Will it look like the system like Gato but scaled? What's your sense of what does meta learning look like? Do you think
Great.
With all the wisdom we've learned so far?
Yeah, great question. Maybe it's good to give another data point looking backwards rather than forward. So when we talk in 2019, meta learning meant something that has changed mostly through the revolution of GPT-3 and beyond. So what meta learning meant at the time was driven by what benchmarks people care about in meta learning. And the benchmarks were about a capability to learn about object identities. So it was very much overfitted to vision and object classification. And the part that was meta about that was that, oh, we're not just learning 1,000 categories that ImageNet tells us to learn. We're going to learn object categories that can be defined when we interact with the model. So it's interesting to see the evolution, right? The way this started was we have a special language that was a data set, a small data set that we prompted the model with, saying, hey, here is a new classification task. I'll give you one image and the name, which was an integer at the time of the image, and a different image, and so on. So you have a small prompt in the form of a data set, a machine learning data set. And then you got then a system that could then predict or classify these objects that you just defined kind of on the fly. So fast forward, it was revealed that language models are few-shot learners. That's the title of the paper. So very good title. Sometimes titles are really good. So this one is really, really good because that's the point of GPT-3 that showed that, look, sure, we can focus on object classification and what meta learning means within the space of learning object categories. This goes beyond or before rather to also Omniglot, before ImageNet, and so on. So there's a few benchmarks. To now all of a sudden we're a bit unlocked from benchmarks, and through language we can define tasks, right? So we're literally telling the model some logical task or little thing that we wanted to do. We prompt it much like we did before, but now we prompt it through natural language. And then, not perfectly, I mean, these models have failure modes, and that's fine. But these models then are now doing a new task, right? So they meta learn these new capabilities. Now, that's where we are now. Flamingo expanded this to visual and language, but it basically has the same abilities. You can teach it, for instance. An emergent property was that you can take pictures of numbers and then do arithmetic with the numbers just by teaching it. Oh, when I show you 3 plus 6, I want you to output 9, and you show it a few examples, and now it does that. So it went way beyond this ImageNet sort of categorization of images that we were a bit stuck maybe before this revelation moment that happened in 2000, I believe it was 19. But it was after we chatted.
In that way, it has solved meta learning as was previously defined.
Yes, it expanded what it meant. So that's what you say. What does it mean? So it's an evolving term. But here is maybe now looking forward, looking at what's happening, obviously in the community with more modalities, what we can expect. And I would certainly hope to see the following. And this is a pretty drastic hope, but in 5 years, maybe we chat again. And we have a system, right? A set of weights that we can teach it to play StarCraft. Maybe not at the level of AlphaStar, but play StarCraft, a complex game. We teach it through interactions to prompting. You can certainly prompt a system, that's what Gato shows, to play some simple Atari games. So imagine if you start talking to a system, teaching it a new game, showing it examples of, in this particular game, this user did something good. Maybe the system can even play and ask you questions. Say, hey, I played this game. I just played this game. Did I do well? Can you teach me more? So 5, maybe to 10 years, these capabilities, or what meta learning means, will be much more interactive, much more rich, and through domains that we were specializing, right? So you see the difference, right? We built AlphaStar specialized to play StarCraft. The algorithms were general, but the weights were specialized. And what we're hoping is that we can teach a network to play games, to play any game, just using games as an example, through interacting with it, teaching it, uploading the Wikipedia page of StarCraft. Like, this is in the horizon, and obviously their details need to be filled and research need to be done. But that's how I see meta learning evolve, which is going to be beyond prompting. It's going to be a bit more interactive. It's going to, the system might tell us to give it feedback after it maybe makes mistakes or it loses a game. But it's nonetheless very exciting, because if you think about this way, the benchmarks are already there. We just repurpose the benchmarks, right? So in a way, I like to map the space of what maybe AGI means to say, okay, like, we went 101% performance in Go, in chess, in StarCraft. The next iteration might be 20% performance across quote unquote all tasks, right? And even if it's not as good, it's fine. We actually have ways to also measure progress, because we have those specialized agents, and so on. So this is, to me, very exciting. And these next iteration models are definitely hinting at that direction of progress, which hopefully we can have. There are obviously some things that could go wrong in terms of we might not have the tools, maybe transformers are not enough, then there's some breakthroughs to come, which makes the field more exciting to people like me as well, of course. But that's, if you ask me 5 to 10 years, you might see these models that start to look more like weights that are already trained, and then it's more about teaching or make their meta learn what you're trying to induce in terms of tasks and so on, well beyond the simple now tasks we're starting to see emerge, like small arithmetic tasks and so on.
So a few questions around that. This is fascinating. So that kind of teaching, interactive, so it's beyond prompting, so it's interacting with the neural network. That's different than the training process. So it's different than the optimization over differentiable functions. This is already trained, and now you're teaching. I mean, it's almost like akin to the brain. The neurons are already set with their connections. On top of that, you're now using that infrastructure to build up further knowledge. Okay, so that's a really interesting distinction. That's actually not obvious from a software engineering perspective, that there's a line to be drawn. Because you always think for a neural network to learn, it has to be trained and retrained. But maybe, and prompting is a way of teaching a neural network a little bit of context about whatever the heck you're trying it to do. So you can maybe expand this prompting capability by making it interact. That's really really
By the way, this is not, if you look at way back at different ways to tackle even classification tasks. So this comes from like long-standing literature in machine learning. What I'm suggesting could sound to some like a bit like nearest neighbor. So nearest neighbor is almost the simplest algorithm that you can that does not require learning. So it has this interesting, like, you don't need to compute gradients. And what nearest neighbor does is you quote unquote have a data set or upload a data set, and then all you need to do is a way to measure distance between points. And then to classify a new point, you're just simply computing what's the closest point in this massive amount of data, and that's my answer. So you can think of prompting in a way as you're uploading not just simple points, and the metric is not the distance between the images or something simple. It's something that you compute that's much more advanced. But in a way, it's very similar, right? You simply are uploading some knowledge to this pre-trained system in nearest neighbor. Maybe the metric is learned or not, but you don't need to further train it. And then now you immediately get a classifier out of this, right? Now it's just an evolution of that concept, very classical concept in machine learning, which is, just learning through what's the closest point, closest by some distance, and that's it.
Yeah.
It's an evolution of that. And I will say how I saw meta learning when we worked on a few ideas in 2016 was precisely through the lens of nearest neighbor, which is very common in computer vision community, right? There's a very active area of research about how do you compute the distance between two images, but if you have a good distance metric, you also have a good classifier, right? All I'm saying is now these distances and the points are not just images, they're like words or sequences of words and images and actions that teach you something new. But it might be that technique wise, those come back. And I will say that it's not necessarily true that you might not ever train the weights a bit further. Some aspect of meta learning, some techniques in meta learning do actually do a bit of fine tuning, as it's called, right? They train the weights a little bit when they get a new task. So as I call the how or how we're going to achieve this, as a deep learner, I'm very skeptic. We're going to try a few things, whether it's a bit of training, adding a few parameters, thinking of this as nearest neighbor, or just simply thinking of there's a sequence of words, it's a prefix, and that's the new classifier. We'll see, right? There's the beauty of research, but what's important is that is a good goal in itself that I see as very worthwhile pursuing for the next stages of not only meta learning. I think this is basically what's exciting about machine learning, period, to me.
Well, the interactive aspect of that is also very interesting.
Yes.
The interactive version of nearest neighbor.
Yes.
To help you pull out the classifier from this giant thing. Okay. Is this the way we can go in 5, 10 plus years from any task? From many tasks to any task. So, and what does that mean? Like, what does it need to be actually trained on? At which point is the network had enough? So what does a network need to learn about this world in order to be able to perform any task? Is it just as simple as language, image, and action? Or do you need some set of representative images? Like if you only see land images, will you know anything about underwater? Is that somehow fundamentally different? I don't know.
Those are open questions, I would say. I mean, the way you put, let me maybe further your example, right? If all you see is land images, but you're reading all about land and water worlds, but in books, right? Imagine,
Yes.
like, would that be enough? I mean, good question. We don't know, but I guess maybe you can join us if you want in our quest to find this. That's precisely
water world. Yeah.
Yes, that's precisely. I mean, the beauty of research and that's the research business we're in, I guess, is to figure this out and ask the right questions and then iterate with the whole community, publishing like findings and so on. But yeah, this is a question. It's not the only question, but it's certainly, as you ask, is on my mind constantly, right? And so we'll need to wait for maybe let's say 5 years. Let's hope it's not 10 to see what are the answers. Some people will largely believe in unsupervised or self-supervised learning of single modalities, and then crossing them. Some people might think end-to-end learning is the answer. Modularity is maybe the answer. So we don't know, but we're just definitely excited to find out.
But it feels like this is the right time, and we're at the beginning of this.
Yes.
Of this journey. We're finally ready to do these kind of general, big models and agents. What do you sort of specific technical thing about Gato, Flamingo, Chinchilla, Gopher, any of these that is especially beautiful, that was surprising? Maybe is there something that just jumps out at you? Of course, there's the general thing of like you didn't think it was possible, and then you realize it's possible in terms of the generalizability across modalities and all that kind of stuff, or maybe how small of a network, relatively speaking, Gato is, all that kind of stuff. But is there some weird little things that were surprising?
Look, I'll give you an answer that's very important because maybe people don't quite realize this, but the teams behind these efforts, the actual humans, that's maybe the surprising, in a obviously positive way. So anytime you see these breakthroughs, I mean, it's easy to map it to a few people. There's people that are great at explaining things and so on. That's very nice. But maybe the learnings or the meta learnings that I get as a human about this is, sure, we can move forward, but the surprising bit is how important are all the pieces of these projects. How do they come together? So I'll give you maybe some of the ingredients of success that are common across these, but not the obvious ones on machine learning. I can always also give you those. But basically, there is engineering is critical. So very good engineering, because ultimately we're collecting data sets, right? So the engineering of data, and then of deploying the models at scale into some compute cluster, that cannot go understated. That is a huge factor of success. And it's hard to believe that details matter so much. We would like to believe that it's true that there is more and more of a standard formula, as I was saying, like, right, this recipe that works for everything. But then when you zoom in into each of these projects, then you realize the devil is indeed in the details. Yeah. And then the teams have to work kind of together towards these goals. So engineering of data and obviously clusters and large scale is very important. And then one that is often not, maybe nowadays it is more clear, is benchmark progress, right? So we're talking here about multiple months of, tens of researchers and people that are trying to organize the research and so on, working together. And you don't know that you can get there. I mean, this is the beauty. Like, if you're not risking to trying to do something that feels impossible, you're not gonna get there. But you need a way to measure progress. So the benchmarks that you build are critical. I've seen this beautifully play out in many projects. I mean, maybe the one I've seen it more consistently, which means we established the metric. Actually, the community did, and then we leveraged that massively, is AlphaFold. This is a project where the data, the metrics were all there, and all it took was, and it's easier said than done, an amazing team working not to try to find some incremental improvement and publish, which is one way to do research that is valid, but aim very high and work literally for years to iterate over that process. And working for years with a team, I mean, it is tricky. That also happened to happen partly during a pandemic and so on. So I think my meta learning from all this is the teams are critical to the success. And then, if now going to the machine learning, the part that's surprising is, so we like architectures like neural networks, and I would say this was a very rapidly evolving field until the transformer came. So attention might indeed be all you need, which is the title. Also a good title, although in hindsight is good. I don't think at the time I thought this is a great title for a paper. But that architecture is proving that the dream of modeling sequences of any bytes, there is something there that will stick. And I think these advance in architectures, in kind of how neural networks are architectured to do what they do, it's been hard to find one that has been so stable and relatively has changed very little since it was invented 5 or so years ago. So that is a surprise that keeps recurring into other projects.
Try to, on a philosophical or technical level, introspect what is the magic of attention. What is attention? That's attention in people that study cognition, so human attention. I think there's giant wars over what attention means, how it works in the human mind. So there's very simple looks at what attention is in a neural network from the days of attention is all you need. But do you think there's a general principle that's really powerful here?
Yeah, so a distinction between transformers and LSTMs, which were what came before, and there was a transitional period where you could use both. In fact, when we talked about AlphaStar, we used transformers and LSTMs. So it was still the beginning of transformers. They were very powerful, but LSTMs were still also very powerful sequence models. So the power of the transformer is that it has built in what we call an inductive bias of attention that makes the model, when you think of a sequence of integers, right? Like we discussed this before, right? This is a sequence of words. When you have to do very hard tasks over these words, this could be, we're going to translate a whole paragraph, or we're going to predict the next paragraph given 10 paragraphs before. There's some loose intuition from how we do it as a human that is very nicely mimicked and replicated, structurally speaking, in the transformer, which is this idea of you're looking for something, right? So you're sort of, when you just read a piece of text, now you're thinking what comes next. You might want to relook at the text or look it from scratch. I mean, literally is because there's no recurrence. You're just thinking what comes next. And it's almost hypothesis driven, right? So if I'm thinking the next word that I'll write is cat or dog, okay? The way the transformer works, almost philosophically, is it has these two hypotheses. Is it going to be cat or is it going to be dog? And then it says, okay, if it's cat, I'm going to look for certain words, not necessarily cat, although cat is an obvious word. You would look in the past to see whether it makes more sense to output cat or dog. And then it does some very deep computation over the words and beyond, right? So it combines the words, but it has the query, as we call it, that is cat. And then similarly for dog, right? And so it's a very computational way to think about, look, if I'm thinking deeply about text, I need to go back to look at all of the text, attend over it. But it's not just attention, like what is guiding the attention, and that was the key insight from an earlier paper, is not how far away is it? I mean, how far away is it is important. What did I just write about? That's critical. But what you wrote about 10 pages ago might also be critical. So you're looking not positionally, but content-wise, right? And transformers have this beautiful way to query for certain content and pull it out in a compressed way, so then you can make a more informed decision. I mean, that's one way to explain transformers, but I think it's a very powerful inductive bias. There might be some details that might change over time, but I think that is what makes transformers so much more powerful than the recurrent networks that were more recency bias based, which obviously works in some tasks, but it has major flaws. Transformer itself has flaws. And I think the main challenge is these prompts that we just were talking about. They can be 1,000 words long. But if I'm teaching you StarCraft, I mean, I'll have to show you videos. I'll have to point you to whole Wikipedia articles about the game. We'll have to interact probably as you play. You'll ask me questions. The context required for us to achieve me being a good teacher to you on the game, as you would want to do it with a model, I think goes well beyond the current capabilities. So the question is, how do we benchmark this? And then how do we change the structure of the architectures? I think there's ideas on both sides, but we'll have to see empirically, right? Obviously, what ends up working in the.
And as you talked about, some of the ideas could be, keeping the constraint of that length in place, but then forming like hierarchical representations to where you can start being much cleverer in how you use those 1,000 tokens.
Indeed.
Yeah, that's really interesting. But it also is possible that this attentional mechanism, where you basically you don't have a recency bias, but you look more generally, you make it learnable. The mechanism in which way you look back into the past, you make that learnable. It's also possible we're at the very beginning of that, because that you might become smarter and smarter in the way you query the past. So recent past and distant past, and maybe very, very distant past. So almost like the attention mechanism will have to improve and evolve as good as the tokenization mechanism, so you can represent long-term memory somehow.
Yes. And I mean, hierarchies are very, I mean, it's a very nice word that sounds appealing. There's lots of work adding hierarchy to the memories. In practice, it does seem like we keep coming back to the main formula or main architecture. That sometimes tells us something. There's such a sentence that a friend of mine told me, like, whether it wants to work or not. So Transformer was clearly an idea that wanted to work. And then I think there's some principles we believe will be needed, but finding the exact details matter so much, right? That's going to be tricky.
I love the idea that there's like you as a human being, you want some ideas to work, and then there's the model that wants some ideas to work, and you get to have a conversation to see which more likely the model will win in the end. Because it's the one you don't have to do any work. The model is the one that has to do the work, so you should listen to the model.